In this session, we will introduce the typical hybrid speech coding technique, code excited linear prediction, CLP coding, which is used, for example, in the GSM standard. CLP is commonly used as generic term for a class of algorithm and not for a particular codec. Code excited or codebook excitation linear prediction codec has a typical hybrid coding scheme, which is originally proposed by M.R. Schroeder and B.S. et al. In 1985. It has better synthesized speech quality and anti-noise performance at bitrate 4.8 kilobits per second to 16 kilobits per second than the LPC vocoder. Along with its variants, such as algebraic CLP, relaxed CLP, low delay CLP, and vector sum excited linear prediction, it is currently the most widely used speech coding algorithm. The basic idea of CLP is to represent the residue after long-term pitch period and short-term vocal tract prediction on each frame by code words from a VQ-generated codebook, rather than by multiple pulses. The residue generator in previous design is replaced by a code word generator, typically 40 sample code words for 5 millisecond frame at 8 kHz sampling rate. It can use either deterministic or stochastic codebook. 10-bit codebooks are common. Deterministic codebooks or fixed codebooks are usually designed using some mechanical methods. For example, algebraic codebook, stochastic codebooks motivated by observation that the histogram of the residue from the long-term predictor roughly is Gaussian PDF. Construct a codebook from wide Gaussian random numbers with unit variance. The CLP algorithm is based on three main ideas. Using the source filter model of speech production through linear prediction LP, using an adaptive and a fixed codebook as the input excitation of the LP model, performing a search in closed loop in a perceptual weighting domain. The short-term predictor removes redundancies in speech signal associated with intra-frame correlations. It reflects the resonance of vocal tract and can be visualized with linear prediction analysis. After the short-term prediction, the speech signal can be represented with a set of LPC parameters and the LPC residue. The long-term predictor removes redundancies in speech signal associated with interframe correlations. It reflects the periodic of voiced speech, that is, vocal cord vibration. In the LPC analysis, the speech signal Sn passes through the prediction error filter AZ and generates the short-term residue Un, which includes primary pitch pulses that can be removed by long-term predictor of the form BZ. Giving Vn is the residue after short-term and long-term prediction. It has fewer large pulses to code than in Un. The main principle behind CLP is called analysis by synthesis, ABS, and means that encoding analysis is performed by perceptual optimizing the decoded synthesis signal in a closed loop. In theory, The best CLP stream would be produced by trying all possible bit combinations and selecting the one that produces the best sound decoded signal. This is obviously not possible in practice for two reasons. The required complexity is beyond any currently available hardware, and the best sounding selection criteria implies a human listener. In order to achieve real-time encoding using limited computing resources, the CELP optimization is broken down into smaller, more manageable, sequential searches using the perceptual weighting function. ABS coding procedure replaces quantizer for generating excitation signal with an optimized process denoted as error minimization, whereby the excitation signal is constructed based on minimization of the mean squared value of the synthesis error using perceptual weighting filter. In CLP codec, the encoder analysis includes decoding synthesis procedure. The synthesis error generated in decoder has been adjusted perceptual when encoding. The synthesis error is computed with waveform matching criteria. Thus, CLP is hybrid codec mixing LPC and waveform coding. ABS coding procedure replaces quantizer for generating excitation signal with an optimization process denoted as error minimization, whereby the excitation signal Dn is constructed based on minimization of the mean square value of the synthesis error using perceptual weighting filter. Basic operation of each loop of closed-loop ABS system includes several steps. At the beginning of each loop, and only once each loop, the speech signal Xn is used to generate an optimal p-order LPC filter of the form Hz. Then, the difference signal Dn, which is based on an initial estimate of the speech signal, is perceptually weighted by a speech adaptive filter of the form Wz. The error minimization box and the excitation generator create a sequence of error signals that iteratively, once per loop, improve the match to the weighted error signal. The resulting excitation signal Dn, which is an improved estimate of the actual LPC prediction error signal for each loop iteration, is used to excite the LPC filter, and the loop processing is iterated until the resulting error signal meets some criterion for stopping the closed-loop iterations. Most modern audio codecs attempt to shape the noise so that it appears mostly in the frequency regions where the ear cannot detect it. For example, the ear is more tolerant to noise in parts of the spectrum that are louder and vice versa. In order to maximize speech quality, CLP codecs minimize the mean square of the error noise in the perceptually weighted domain. As shown in the figure, as the parameter gamma in denominator of Wz approaches 1, the weighting function is flat. As gamma approaches 0, the weighting function becomes inverse frequency response of vocal tract. In order to make the perceptual weighting be less sensitive to the detected frequency response of the vocal tract filter, the perceptual weighting filter is often modified to another form. The weighting filter is applied to the error signal used to optimize the codebook search through analysis by synthesis. This results in a spectral shape of the noise that tends towards the inverse of WZ, which is called noise shaping filter. Well, the simplicity of the model has been an important reason for the success of CLP. It remains that WZ is a very rough approximation for the perceptual optimal noise weighting function. The figures illustrate the noise shaping results of error spectrum without and with the perceptual weighting filter. In CLP encoder, the modeling is divided in two stages. A linear predictive stage that models the spectral envelope, and codebook-based model of the residue of the linear predictive model. Short-term predictor with LPC analysis is used to predict the intra-frame correlation and leads to LPC residue. Furthermore, the long-term predictor is used to predict the periodic component for voice signal based on the short-term residue and leads to adaptive codebook. After the long-term and short-term predicting, the final residue is expressed by stochastic or fixed codebook. The CLP model is based on source filter model. As can be seen from the CLP decoder illustrated in the figure. The excitation is produced by summing the contributes from an adaptive, also known as pitch, codebook, and a stochastic, also known as an innovation or fixed codebook. The fixed codebook is a vector quantization dictionary that is implicitly or explicitly hard-coded into the codec. This codebook can be algebraic in ACLP-based codec or be stored explicitly, for example, in SPIX codec. The entries in the adaptive codebook consist of delayed versions of the excitation. This makes it possible to efficiently code periodic signals, such as voiced sounds. Populate codebook from a one-dimensional array of Gaussian random numbers, where most of the samples between adjacent codebooks were identical. Such overlapping codebooks typically use shifts of one or two samples and provide large complexity reductions for storage and computation of optimal codebook vectors for a given frame. As is shown in the figure, the two code words in the overlapped stochastic codebook are identical except for a shift of two samples. That's all for this session. See you next session.